welcome from me as well. It's my privilege to open the 8th the Cannafest myself. And I'm also happy that you found it because I was perhaps the first comer and I had problems spotting the access. So congratulations. Allow me to introduce myself. My name is Josef Krejčík. My nickname is Mr. José. I publish books and articles in different magazines on this issue. I also am a professional advisor for companies who commercially grow cannabis, and I'm holder of the patient focus certificate, which is about growing the medical cannabis. And apart from that, apart from writing books about growing cannabis, I have recently specialized in testing different types of illumination. And that's really the reason why I'm here today. I lectured 4 years ago about artificial illumination at this festival. In those days, I started with testing different sources of light using special spectrometer. And this year I repeated the test because over the past couple of years, the progress in illumination has advanced. We have functional LED illumination source, which can be used as well. And another reason why I repeat the test is that in the past I use magnitude called photosynthetically active radiation in watts per meter square. And this is no longer used today. We have a more accurate unit for measuring the energy of light in photons impacting a specific area. In our case, it's again meter square. And for us growers, this is more important, and I will explain why and how, or what these magnitudes are about.
And then we'll come over to the results obtained with the various lighting sources used in our measurements. Just a while ago it functioned properly, and now it doesn't. It seems to be all right. So this is the basic difference between the perception of light by us, by humans, and the perception of light by plants. Because of this difference, we can't use lighting destined primarily for people, use them for plants. Well, we can use them, but it's not as effective as if we use lighting directly destined for plants. Plants are most sensitive to lighting within 400 to 500 nanometers, and 570 to 700, which is the other peak. And it is because of this we have established a term which we call photosynthetically active radiation, which is that part of the wavelength spectrum from 470 to 700 nanometers used by plant for photosynthesizing. A photosynthesis, it's a complex process, but of course we can say that they're using light, CO2, and the nutrients to grow. They're using it for growth as a source of energy. If we want healthy plants and a good yield thereof, we need proper photosynthesis. And correct lighting is an indispensable part of it. Lately, we've heard voices that we should be using the term photobiologically active radiation. Photobiologically active radiation should designate lights from 270 to 800 nanometers. We don't even have that range here. The reason being that today we already know that UV radiation, 280 and above, that it influences in a way the development of the plants as much as it's influenced by longer wavelengths up to the 750, 800 nanometers. Basically, both these spectra, which are not shown here in full, then using these spectra we can obtain a greater content of effective substances or species, active species. You know, if we act on cannabis by this type, we obtain a higher percentage of cannabinoids and others, but that would amount to a separate chapter. So let's approach an explanation of the unit I am going to use so that you can understand the results, which I'd like to show you. Well, each light-emitting source emits plenty of light of different wavelengths. Some of this light reaches outside the spectrum of the photonic length, which can be characterized as photosynthetically active. Imagine that a light bulb used for illumination of plants emits such a quantity of lights of different colors. And imagine that, for illustration, I've taken a handful of these multicolored candy. Imagine that each of these candies is a photon. It stands for a photon of a different wavelength: blue, violet, red, yellow. And now just imagine it's only those orange ones are within the range of the photosynthetically active lighting. So imagine a bulb which emits that many photons, but we have no more than 6 orange ones. Only 6 orange photons are active and can be used by that particular flower. If I take that handful and pour it onto it's only the orange candy that can be used for photosynthesis, while all the other ones are sort of destroyed. They've used up some energy because I have to source the light source in order to transform electricity to light. But what I only need is just those 6 orange photons. Having poured out this of my handful, we can say that out of the light, the photosynthetically active photons are just 6 of them. This is why we are using the photosynthetic flux. ppf is the abbreviation or the symbol. We have 6 of them, so we can say that ppf for this type of lighting, let's imagine this as a multicolored lighting, is ppf6. If I were to produce light for plants, I could say that my lighting will emit ppf6 per second. But we are not only interested in how many photons or photosynthetically active photons are emitted, but we like to know how many will impact upon the plant. So let's focus on the orange ones only. The handful is poured out, containing 6 photons which are active, which I need, but only 4 of them would hit the plant, because some of them would fall on the wall, some of them would fall on the ground, not all of them would hit the plant. And that is what I need to know as grower. It's cost me some money for electric power, and I'd like to know how many photons am I going to use finally. And that's what we are talking about. 6 have been emitted, 4 impinged. 6 is ppf, And the 4 is photosynthetically active flux, ppfd density, micromole per millimeter square per second, or meter square per second. I hope I've clarified this sufficiently. So let's now approach what it means for us. That is, what values do we need actually? You can see the 4 categories which we are using normally in growing, at cars, seedlings, the cuttings, okay. Then I have the growth phase, and we have the flowering phase. For the cuttings, we need ppf D60 to 250 micromole per meter square per second. For the mother, we see 500. For the growth phase, 5 to 700. For the flowering phase, 700 to 1,000 and beyond. 1,000 because in the world there is one excellent light-emitting source, which, if we are lucky, we can see every day, of greater power than any other. If we have sunshine, summertime or wintertime, we can measure ppfd 2,000 micromole per meter square per second every day, if there is sunshine. If there's no sunshine, if it's just behind a cloud, even a smaller cloud, we only get 1/10 of that quantity. In this way, we can explain why we need 1,000 and more for the flowering phase. In the nature, outdoors, particularly at our latitudes, but in fact, on most of the Earth, it's not that we have a clear sky all the time. So if we were to let the plants be hit by 1,000 or 2,000 per meter square per second, they can stand it. They are adapted to it. They can absorb it. But inasmuch as we, in case of indoor growing, we can have a clear sky, in fact, all throughout the period. We don't need that high values. We can make do with around 1,000 micromole per meter square per second. In order to be able to measure the photosynthetic flux density, I can't use an ordinary lux meter or a sensor which is primarily destined or designed for humans. But we need a special spectrometer. We can even call it a palmeter, because that is what it measures. And 4 years ago, I've rented in order to be able to obtain this data, and that was quite costly. I purchased a spectrometer of my own. It's not just the very most expensive equipment, but it's still powerful enough and precise enough to be able to perform these calibrated measurements from a German supplier. It's not Chinese or not any. Another thing I had to do to resolve, I had to use a certain growing area, 100 centimeters. And in my first measurement, I've determined that if I just move the sensor a little bit aside, 3-5 centimeters to one or another side, the results obtained are different. So what I've done is I've designed a special plate where I inserted the sensors and tried always to have it in the same place. So 4 years ago, This was a positioning system where I was in the tent and I kept adjusting the position of the sensors to this or that opening aperture. But this year I've done it differently. I have had such a contraption designed, a computer-controlled sliding system, which always will put my sensors in the same position. So perhaps if my colleague could activate it, please try. Or it's just a picture. The video is gone. We can't get it. We can't get the video. That's in this way. This is, of course, accelerated. 36 points, discrete points, in which positions in which I have measured the ppb value, the photosynthetic active photons flux density, so as to best cover the entire growing area. So I've noted, I've registered the values in 10 centimeter spacings, and I produced this table. This is how the sensor kept moving. So I had a recording for each of the positions, and out of this table I've produced this graph. This is a graphic representation which shows different colors. Whatever is beyond 1000 is red, whatever is beyond 1900, that's near the sunshine, is violet, and what's under 300 is weak, truly weak. It's only good for the colonies, so it's in black. From this moment on, as the graphics can show, I think it's clear to everyone. Okay, it is. So let me talk about the results. One point of that should be paid attention to: the maximum and the minimum ppb values. These figures are all quite important because you can see for yourselves in this graph that the highest intensity lighting is in the middle, whereas near the edges it's weaker. Obviously, here the minimum is 500-600 per meter square per second. It's not that bad, but still the results are worse. And I'm interested in learning for different light sources what the average would be, what it would tell me, what these three figures would tell me about the uniformness of distribution of lighting over the growing area. And now let me approach the practical results. I've begun by the generally used lighting, 400 watt discharge bulbs, high pressure sodium discharge bulbs. So that's quite normal, but I've just focused on the results. So at 400 watt output with an appropriate ballast resistor, you have to compare the electrical, or rather the electronic, the electrical ones are much more powerful than the magnetic ones. The difference may be as much as 30%, but on the average, they give 15% more light at the same electric power consumption. That's quite a lot. These ballast resistors, of course, cost twice as much. They are more expensive, but it pays for us in terms of results. So to invest in a better ballast resistor is useful, and it also less maintenance, less defects. As a reflector, For all or for most of the sodium discharge bulbs, I've used this medium-sized type, and here is the result. I've tried the sodium bulbs at different distances from the source. The optimum distance for the 400 watt bulb is about 30 centimeters, which corresponds with the practical distance where you don't burn the plants, but at the same time uniformity is good enough so that the entire area is well lighted, even though on the edges it's lower than 500. But that's what's normally used. It works. The minimum values 350, 476, that's not bad. But from my point of view, a 400 watt discharge lamp is the best solution in terms of energy savings. Just as a matter of interest, if you put it at a greater distance, increase the distance, but just 10 centimeters, which is not much. So the drop is 10% on the average illumination. If we use the foregoing picture, it's 676, while here is 607, and it's only a mere 10 centimeters. So every centimeter has its place, has its effect. So in growing, you've got to think about this. Every centimeter is important. 600 watt, also with an electronic ballast, 40 centimeters distance. Of course, a 600 watt bulb has to be placed at a greater distance, but that distance again is a practically, it flows from practical experience, and the results were very good. The average was 901, which is very good, quite a good result, the ppfd, but wherever it's beyond 1000, the size of this trace beyond 1000 is much greater, much more extensive, so you can see that the flowers get much more intensity. Of course, the yield will be better of the crop. Again, a distance greater by 10 centimeters, the area will be illuminated by to a much lower density, again 10% less. So it works out beautifully. 10% is the difference. As a matter of interest, I also show you a comparison of an ordinary electromagnetic ballast resistor with the use of a fully electronic ballast resistor. 40 centimeters, the same path, the same distance, but a different ballast. It's an electronic one, and this is the electromagnetic one. You can see that the difference is about, again, 15%, as I've mentioned it before. So I'm getting a savings, but then I'm getting a loss. For 1 meter square, you can also use a 1000 watt sodium lamp, which is not usual for 1 meter by 1 meter. It's more usual for 120 by 120. But people do use it, and then again the yield is even greater, because you can see for yourselves that simply the plants are getting more light. We do have the 1000 watt sodium lamp, but we'll be comparing it with LEDs, so we can use it as a baseline. There's a 1000 watt lamp placed at a distance greater by 10 centimeters. Again, 15–20% difference. Recently, sodium lamps, double-ended sodium lamps have appeared, specifically at the wattage of 1001. It's quite common. So I'd like to know whether there'll be a better effectiveness of illumination. So what will be the scattering of the light? What will be the distribution? Because one of the properties is that the ordinary sodium lamps, which are rotating, they have, well, the lighting trace. You can see it here, for example. If I shift it, if I move it, I always will have a point somewhere which will be influenced by the shape of the lamp, of the discharge lamp. But that's what the manufacturers told me. So there's a shift and there'll be a difference. You won't see that much in the case of the 1000 watt lamp. But I've also tested the double-ended lamp. You can see the trace or the pathway. Out of all those I've shown so far, the uniformness is best here, and the minimum is just below 1000, which we have set 1000 for the high blossoming, high flowering phase is the best. So if I sum it up, people would normally use, again, I've moved it 10 centimeters and it's decreased. What I have here is a comparison of the 400 watt, 600 watt, and 1000 watt sodium discharge lamp, the last being a double-ended lamp. And we still speak about meter by meter, 1 meter by 1 meter, but you can see the difference. For effectiveness, in terms of effectiveness per meter square, you can see that the 600 watt lamp is the ideal one. But with that has the power of 1000 watt, of course the yield is higher. But the area 1 meter by 1 meter does involve its limits. You can't go beyond a certain limit. So if you use 1000 watt instead of 600 watt, but still there is a growth, but not that much. One more thing I'd like to tell you. Most of those 1000 watt lamps can be switched to a lower output. It does have a switch between 1000 and 600 watt, so you don't have to use 1000 watt all the time. And that, of course, will markedly increase effectiveness, because I'll let it go at full blast for 1000 when I expect the highest growth rate of the flowers. In 2017, you've certain to have heard about the LED lamps. So I have been able to include several light sources of this type, because the manufacturers are already willing to let you have to loan you some of these lamps. So this is a catch, because this is a very expensive module. So I've decided not to disclose the name of the manufacturers should it happen that the results would be less than expected. But it costs much more than 1,000 euros, so it's quite a high price. And the manufacturer of this module promises 2000 micromole per meter square per second and more. So they were not lying, it was the truth. But you can't do it on such an area. Then this is at the distance of 30 centimeters. But you know, the field has corners, has angles. So this is 290 watt. 30 centimeters away. The minimum is 90. And that, of course, is not enough. While here in the middle, we had more than 2000. In our experience, as long as the values are beyond 1 or 2,000 micromoles per meter square per second. The plant will lose color, and they have white colored tips, which is not good. The plant is no longer green. If it's not green, photosynthesis can proceed unimpeded. Okay, so it does have a limit, it does have a concentrated output. So let's try to put the module at a greater distance, 50 centimeters away above the, and use the same sensor. And there's a lot of area here which hasn't get enough illumination, but the minimum has increased to 93. Having put it even higher, 70 centimeters away, here the minimum is 151, but you can see for yourselves that in fact the plants won't be getting enough light. They'll be getting too much in the middle and not enough along the edges. And this problem concerns with a long series of plots which are of rectangular shape, and the lighting sources also are rectangular. If it's in pots, perhaps, so you use this to increase illumination. You need it to take up as little space as possible so that it wouldn't shade the primary lighting. But when applied indoors, where it represents the sole lighting used, the LED modules have proven well, which are of an elongated shape. So the distribution of the light is much better. So for the indoor growing, the results are better, and work is easier with these elongated ones. Just at random, I've taken 2 times 140 watt, which is in fact which corresponds to the one of 290 at a distance of 20 centimeters, because I can put them close. I needn't be afraid of not having enough illumination along the edges, because otherwise I'd have too much in the middle, but I'd have a large area not illuminated enough. Whereas with these elongated modules, I've been able to put them at a greater distance or at a lower distance, and out of the 290 watts, I've been able to obtain much better results than with the previous type. Here, for demonstration, this is a comparison of a 400 watt sodium lamp. This is the rectangular module 50 centimeters away. And here at the bottom, it's 2 modules using the elongated shape. You can see that the light distribution, and in fact, is much more uniform. We don't have that high intensity here, but what we do have is a good scattering. So on average, you can see that in fact we are getting much better results on the average than with the module which is not elongated. If we increase the output, so I've added a 3rd module this way. This is I've got 420 watt total, but I have something. So I have a longer service life for the modules. What I can do here, I can start thinking of using this instead of a 600 watt module. And so what I'm getting at is that many manufacturers would be telling people that they would save 50–60% of energy, but this is not true. This only works here for humans. If it's lighting, if it's luminaires intended for humans, but not for plants. Practice has shown that when using high-quality LED modules, we can save something like 30%, but never 50% or more. I trust that this will keep developing and moving ahead, but at the moment, this is what you can reckon with. So if anyone thinks about replacing your 600 watt sodium with a LED module, so don't buy this one. Here, this is a comparison. What we have is the ordinary 600 watt with an electromagnetic ballast resistor, and this is a 420 watt one of elongated type LED modules. Have a look at the figures. The average, the average values are very similar. It's only several percent difference, but we can demonstrate that if I have a classical ordinary 600 watt sodium lamp used by most people, I can, there's no problem replacing that with a 420 watt LED module, or rather using 3 modules of 140 watt each. If I put this alongside an elongated 280 watt LED module, then just try and imagine. This is here. And let's have a look at how this looks like. Somebody will tell you, a manufacturer will tell you, if you replace a 600 watt with a 300 watt module, so this is the result. So it's not true. You can reckon on 30% saving. Yeah, I've tested other modules as well. There are 2 modules like this. Each of them has 320 modules, 320 watt output. This is a highly professional equipment, but you can note that these modules have no fans, no fan blowers. But that's another thing I like to tell you. That's what I've learned, that if you use LED modules, it is important that the chip chip does not overheat. So you've got to cool it. If it's warmer than 60 degrees C or something like that, then the activity of the LED module is much lower. It won't any longer produce as much light as promised by the manufacturer. And as expected, there are 2 types of cooling. One thing is active cooling using air. It's air-cooled, where on the LED modules you have fans that would cool the control board, the chip. So for one thing, it consumes more electricity. Then it's something like a vacuum cleaner. It's not silent at all. And besides, it will bring in dust, so that the cooling becomes less effective. And it's very, very rare that you can use it, that it won't absorb any humidity. Passively cooled LED modules have to be well designed, because for passive cooling you need an amount of material, in this case iron or aluminum, to carry the heat away from the chip. So this is a passive cooler. But all electricity in this case can be utilized for light generation, not for the cooling effect.
Now, what is the result of my testing? This is the module I showed you. This is LEDs, and the result is very positive. And you can see just 330 watts each. And the pattern is the same as if we have 1000 module, but I used only 660 watts, not 1000 watts. And this is 60 centimeters distance. I use this distance in order to make sure that it will be as far as the 1000 module, and then I brought it closer, 30 centimeters. And I can do this because there is no heat generation, no burning of the plants. And you can see that I've obtained real good values. Just for comparison, 1000 double-end discharge bulb and LED module 660 watts. You can see the only difference is that here we measured lower minimum value, but it's negligible. But maximum and average, the LED module, which could replace the 1000 bulbs, was better off. Well done. Thank you very much for your attention, and enjoy Cannafest. I'm sure that there are many more interesting presentations on the agenda. Thank you.